Well, good afternoon, everyone, and it's a real pleasure to have our third in this series of webinars that are being organised and arranged by our associate editors of the journal. I don't want to take up too much time. I'm going to hand over to Luca in just a brief second, but I would like to take this opportunity just to encourage you to visit the website of the journal, the Data-Centric Engineering Journal, and really consider submitting some of your work to the journal and contributing to what is essentially a transformation of the engineering sciences, the engineering disciplines, and the associated professions. And this transformation is being driven by data and the synthesis of data and our understanding of the underlying science itself. So do please visit the website and do get in contact with either myself or any of the editorial board if you've got any questions about the journal. I'm absolutely delighted that we've got Gianluca from Stanford joining us today. It's a real privilege that we're able to attract speakers of such caliber and ones that can really provide very interesting and topical and timely presentations. So let me hand over to Luca Magri, who will introduce our speaker for today and host the rest of the session.
Right, well, thank you, Mark, and thanks much, Gianluca, for accepting our invitation to give a talk. So Professor Iaccarino is a professor in mechanical engineering at Stanford University and director of the Institute for Computational and Mathematical Engineering. He completed his PhD in Italy at the Polytechnic of Bari in 2005, and then worked for several years at the Center for Turbulence Research, NASA, Ames, and Stanford, before joining the faculty of Stanford University in 2007. So since 2014, Professor Iaccarino has been the director of the PSAP Center at Stanford, which is funded by the US Department of Engineering. It's a very large center, a multi-million-dollar center focused on multi-physics simulations, uncertainty quantification, and exascale computing. Professor Iaccarino won a lot of prizes, but I think one is particularly stands out, which is he received the Presidential Early Career Award for Scientists and Engineering, PCAS, awarded directly from former US President Barack Obama. And also he won a lot of Best Paper Awards, named Best Paper Awards in AIAA, ASME, and other prestigious conferences of the field. So his broad interest in research are data-driven methods, computing, biomedicine, aerodynamics, propulsion, design. And today he's gonna give an overview of his research. All right, thank you very much, Gianluca. Over to you.
Thank you very much, Luca. Let me start sharing. Okay, I think you should be able to see my slides. So thank you again for your invitation and for giving me this opportunity to share some of our work. This is mostly work carried out by my graduate student, Jan Eise, and by one of my postdocs, Ashwin Mishra. The work revolves around the analysis of turbulent flow simulations and try to understand the predictive capabilities of simulations of that kind, and uses both uncertainty quantification ideas and, more importantly, concepts driven and related to data in various ways. So let me first give you a sense of what kind of challenge we have in front of us. Many of you might be familiar with the turbulent flow and specifically turbulent flow simulations, the idea of capturing the complexity driven by the nonlinear and the chaotic nature of fluid dynamics. Now, in this particular setting, we have the advantage of having a set of equations and a conceptual description, mathematical description of the model that is well understood, these Navier-Stokes equations. And there is really no uncertainty in that, at least from the applications we have in mind. With the caveat, though, we need to resolve a very broad range of temporal and spatial scales. And so this means that the calculations, like the one that you are seeing here in this slide, are very, very computationally intensive. Now, what you're seeing here is the simulation of a flow in a diffuser, very, very simple geometry used in a number of propulsion systems. Is a way to slow down actually the flow coming from the left to the right with this sort of opening of the passage. And the interesting aspect of this problem is that from an engineering design perspective, the questions about design of these devices, of these diffusers, are very simple. And it sort of boils down to the question, does the flow separate? And if we're able to answer that question and change the design and improve other characteristics of the design without introducing separation, we have basically accomplished a major design goal in a certain application. Now, as I said, the problem is that simply resolving the scales of this problem are computationally intensive. And also this simulation obviously generates a tremendous amount of data to answer a very simple question. And so the community has developed a number of strategies to cope with this problem. Specifically, the one that we'll be focusing in this talk is the idea of directly representing the time averaged features of this flow. So derive a set of equations that now are engineering equations, meaning that are simplified version of the original equations. And unfortunately, because the equations are not linear, the Navier-Stokes equation to start with, when you introduce this averaging operation, we're making an assumption, we're making an approximation. And so it turns out that the challenge in this problem is how to construct a model, in this case simply an additive model, that can be can augment this set of modified equations to reproduce the results corresponding to the real set of equations, the original set of equations. Now, in the context of this type of problem, say the diffuser flow that I was showing you before, we actually can describe that model, again, analytically as a divergence of a tensor. The tensor is called the Reynolds stress tensor. And at this point, this is all we can say mathematically. There are some mathematical properties about that tensor, but we need to introduce assumptions and empirical models or some other model that allows you to represent that quantity Rij, that tensor, that 3x3 tensor, to provide the ability to actually close these equations and then solve them in a efficient manner. Now, it turns out there are a number of ways to write this Reynolds stress tensor, and in general, we do need, as I said, a number of additional or auxiliary relationships that allow us to derive what I call a computable model, something that can be directly used for predictions without any additional information about the specific test case that we are considering or the problem we are considering. Now, if I fast forward and I use one of these models, and I'm not going to give you details of what specifically this model is, I end up with results that might look like this. This is, again, our diffuser. These symbols, these solid dots there, are basically our prediction for velocity profiles and illustrate the fact that the velocity is positive. So there is basically no separation. And this is what this kind of computation can tell us. Now, as I said, the advantage compared to the original movie I was showing you is that this is a simulation that runs on a laptop in a matter of perhaps a minute, compared to the original simulation that resolved all the scales that might take several hours on a supercomputer. So from an efficiency perspective and the ability to answer that engineering question, at least we are in the ballpark, we are in the right space. But the question is this accurate? Obviously, is the prediction accurate? Now, it turns out that if we have experimental data, we can confirm that. And in this particular case, I'm showing you the same experimental, at the same experimental location within the diffuser, the measurement with the red symbols. And you see that there is obviously a very extensive discrepancy between the prediction in black and these dots. But more importantly, as you see on the bottom, on the sloping side of the diffuser, you see that there is actually red dots that go beyond that sort of gray line that sort of correspond to separation. And so it turns out that the simple engineering model is fast is effective in terms of giving answers, but gives us wrong answer in this case. And so at this point, the question is, what do we do next? Well, we can, as good computational scientists, we need to check certain parameters that we have in our simulations. For example, the grid resolution, this is on your left, the sensitivity to the effect of, for example, inflow distortion that might be present in the system. And so we did this in these two images here that show you that under extensive grid refinement and under quite a bit of variation of velocity, incoming velocity, we still see no separation with this model. And so it turns out that in the absence of experiments, at this point, we will be concluding that these predictions are really telling us that there is no separation, and obviously this will be a very misleading answer. So at this point, the question is, what do we do next? Well, one of the things that we've been focusing on in the last few years is try to understand if we can characterize the uncertainties present in this simulation. Obviously, the simulations are based on a conceptual model that is based on assumptions, and these assumptions might or might not be true. And so the idea is to try to understand if the introduction of an assumption automatically or inherently introduces uncertainty. Now, in this review paper, we actually looked at a variety of ideas related to both uncertainty quantification and data science. And I'll very briefly mention a few ideas that we used in some of these simulations, the simulations of the kind I showed you. So let's start from uncertainty quantification. As I said, the basic underlying assumption is the modeling of these Reynolds stress tensors, these 3x3 symmetric positive definite tensor. Now, the fact that it is symmetric and positive definite means that we have some mathematical constraints that we can use to characterize this tensor. They're not sufficient to define it, but they're sufficient to constrain it. Right? So the way we do it is to introduce an eigenspace decomposition. So simply the eigenvalue and eigenvectors of this Reynolds stress tensor. In this case, the quantities you see on the right-hand side of this formula are K, which is the turbulent kinetic energy. More importantly, or at least in this context, is the trace of the Reynolds stress tensor. Delta J is the Kronecker symbol. Lambda is the 3x3 matrix of the eigenvalues of this matrix, and MV are the vectors, the eigenvectors, basically. The V in and VJL are the left and right eigenvectors. So what you basically at this point, we still have an unknown quantity. So as I said, Rij is unknown. We need to model it. We simply introduce a transformation. And it turns out that this transformation sort of lead us to the description of the Reynolds stress tensor in terms of this ellipsoid, where the ellipsoid can be characterized once again in terms of a shape, an alignment, and a size, which correspond once again to eigenvalue, eigenvectors, and trace of the tensor. And we can actually now start thinking about what are the implications of these mathematical characteristics of the matrix on the actual turbulence. And it turns out that in the literature, this has been studied to some degree, and we know that there are actually direct connection between, for example, the orientation of this ellipsoid and how it affects certain characteristics of turbulent flow. Now, from an uncertainty quantification perspective, though, we can do something a little bit different. What we can do is to say the Reynolds stress model is actually described in this way, but as I said, is an assumption, is a model. So effectively, what we can do is to actually study models that are similar to this model, to this baseline model, or if you like, we can derive a family of models that are actually modified version or perturbed version of this original one. Now, it turns out that, again, because of these particular characteristics of the Reynolds stress, the symmetry and the positive definiteness, we can actually identify bounds on the eigenvalues of these Reynolds stress tensor. What these bounds mean is that the ellipsoid can only change in certain ways, and the depiction of this triangle on the right sort of identifies the way this ellipsoid can change. Obviously, you can think of the top corner as being a sphere. That's obviously one typical state, or one possible state, I should say. And then the other two corners, these sort of noodle model, noodle shape and disc shape, are the two other extremes. Well, it turns out, and the interesting thing about this triangle is that through a linear transformation, you can actually obtain all these states just by, again, changing and modifying the position in which you are in this triangle, and the position is directly connected to the eigenvalues. Okay, so it turns out what the logical idea here is that if we fix the eigenvector, so the orientation, we can actually navigate this entire triangle, which are basically all the possible eigenvalue sets of a turbulence model, just by modifying the eigenvalues, basically, just by linear combinations of these three extreme states. Now, the idea that we had is to actually use this mathematical constraint, and as I said, this possible linear combination of the three corner states to obtain everything else as a way to actually define an error model or a perturbation model to the original Reynolds stress model. Now, we did that in a very straightforward fashion. So if you think of the picture below, the original baseline model will have a certain prediction of the eigenvalues. Let's call it X. Then we decide to perturb along one or towards one of the corners. So this delta B represents how much we are moving, for example, with respect to or towards corner one. And then we obtain basically through this perturbation a new eigenvalue space, eigenvalue set, which is X star, which then is used to reconstruct a new Reynolds stress tensor. Okay, we do this basically everywhere in the computational domain, and we can now build a family of predictions. Starting from the baseline, we can perturb in any way we like and obtain a new prediction, a new model that predicts a state of a solution state, if you like, that is somewhat related to the original one, but perturbed in a very, very specific, very controlled manner. It turns out we actually perform this simulation by perturbing along this direction, but simply combining basically three independent simulations where we perturb all the way to the three corners of this triangle. And the idea is that the range of the simulation that we obtain correspond to at least a measure of the uncertainty present in the simulations. So if we do that, and as I said, we compute additional solution. I'm reporting here basically the original one, the baseline solution, the black, and then these gray areas are basically the one obtained by carrying out three additional simulations and then taking the mean and max of those simulations to build these envelopes. Now, what you see immediately here is that the envelopes are actually illustrating a measure of the uncertainty. Interestingly enough, the experimental data are somewhat falling within this gray interval or gray envelopes, which is a good indication that the original baseline model is incorrect. We knew this already, but perturbed models are actually able to cover that discrepancy between the original model and the experiments. And so the intention here is to illustrate the fact that wherever these envelopes, these ranges are very large, the implication is that the uncertainty is large, and in fact, the error in this case is large. But these kind of envelopes can be computed independently of the availability of experimental data. And so in a general setting, even if you don't have the data, you can use this method, and we used it in a variety of applications to have an indication of how much uncertainty we expect in those regions. Now, the question is, so we are able to do this in a relatively straightforward and effective, cost-effective fashion. But the interesting idea is that at this point, we are only using basically theoretical construction based on the properties of this Reynolds stress vector. There is a fundamental limitation, though, the fact that we are perturbing everywhere in the computational domain in the same way, meaning that we are either perturbing towards one corner or another corner or the third corner, and everywhere in the computational domain, the perturbation is basically to the limit of the triangle that I was showing you before. Now, what this does, the problem with this is that it leads to an overestimate of the uncertainty, because even in regions where perhaps the model is not incorrect or is not introducing a large error, we're still sort of imposing large perturbations. And so the next question is, how can we actually be more parsimonious with these uncertainty envelopes, with this uncertainty range? And how can we parameterize the uncertainty estimates, and specifically these perturbation ranges to some additional information that we might have available. At this point, we have not used any data to calibrate the model, but we can obviously try to use some additional information to build a more precise version of these perturbations. And so in the past, we've used Bayesian updating to introduce a better estimate of those uncertainty informed by data. What I want to show you today, how we are doing it directly from data. Now, I also want to point out, this is a little bit different from some of the application of machine learning and in general, data-driven models in turbulence modeling. We're not trying to improve the model per se. The model remains the model. What we're trying to do is to use data to reduce the uncertainty that is possibly present in the model. So that's at least fundamentally different, because at least from our experience so far, it seems to be a much more generalizable solution to try to reduce the uncertainty rather than improve the model directly. So let me tell you how we did it. So the starting point is that we have some database of trustworthy information. So in this case, typically we have high fidelity simulations like the diffuser I was showing you at the very beginning of this talk, and in general, high fidelity simulation of turbulence that we can use as a reference. And so by performing both engineering simulation, run simulation, and comparing to these high fidelity data sets, we can build a discrepancy function. So an actual distance between the engineering prediction and the high fidelity prediction. Then the next step is to parameterize the run simulation in terms of some features. Now, this is important because obviously we cannot build geometry or physical space dependency. We need to build dependency with respect to quantities that are actually computable in general. They can be used in any configuration of interest. Now, the type of strategy we are using for machine learning, at least in this talk, is a random forest. The random forest predictor is basically a function that takes the features and takes some hyperparameters and provides you a measure or a description of that discrepancy, or is able to represent that discrepancy. And as you know, the strategy is a training optimization strategy that allows you to build these hyperparameters, minimizing some sort of a loss function. In this case, again, just a distance between or the discrepancy function that I was showing you before compared to the high fidelity data. And again, the output is basically these parameters of the random forest. Now, just to be a little more specific, I want to give you a graphical view of what we are trying to do. So from a practical perspective, what we have done before without data is to say, I have a baseline model. The baseline model is predicting some states within this triangle, specifically this line. The theory and this idea of properties of the matrix tell us that in a sense, all the states within these triangles are possible. And so we go from that, those states to basically the entire triangle. Now, what we are trying to do here is a little bit different, because with data-driven model, what we can do is we start from the same place, but now we use DNS data, in this case, a truth model. We compute a distance between the baseline model and this truth model. We parameterize it through this random forest setting. And then effectively, our perturbations are now limited. They can only be applied in a smaller set of the original triangle. And this sort of constraint is exactly what does allow us to take the uncertainty and reduce it. And so the only other thing I want to say is that we used a simple data set. I'll show it in a moment what the configuration is. The discrepancy is based on distance in the eigenspace, eigenspaces, specifically distance in the triangle, in the triangle that I was showing you between the truth model and this runs model. We use 13 features, actually it's 12 there, I apologize for that. We use 12 features to parameterize the runs flow field. And as I said, we apply a random forest regression model. So just a quick word on how we did this. We are using OpenFOAM as a fluid flow solver, and we're using OpenCV as the software for machine learning. Specifically, the choice here is important because we are very interested in online prediction. We're interested in actually building models that we can run very quickly. And in this case, it turns out that OpenCV is a very simple to interface to an existing C and C++ code, but also quite effective in terms of performance compared to other choices that are more common in different applications. Just to give you a sense of the training and testing set, this is the problem, the data set that we've been using. So it's a flow over a wavy wall. So it's a different separated flow, a different geometry. And what I'm showing you in the picture on the bottom left and in the center are the original discrepancy function. So what is the distance in the eigenvalues between the high fidelity and the runs prediction? So the distance is basically an actual measure. So blue means that the two predictions are actually quite close. Yellow and green, the predictions are larger. And now these discrepancies then predicted and mapped using the random forest regressor. And you can see, at least, visually they're very good. And the plot on the right shows directly the prediction versus the expected discrepancy. So we cannot actually see that these random forests are able to parameterize this discrepancy in a very effective manner. We studied the sensitivity of this prediction to a number of parameters that are used in the random forest. The most important one is the parameter on the x-axis, how many trees we are using. And as you can see, going all the way from 50 to 200, in a sense, this is not really changing the prediction. There are a lot of things on this plot. I'm not going to say too much. If you have questions, I'm happy to answer. But we wanted to make sure that whatever prediction we use is not very much affected by the parameter we're using. And as I said, the number of trees is very important because obviously the computational cost of the machine learning model, in this case, is linearly proportional to the number of trees. And so if we can use less and less tree, our online prediction will be much faster. And so obviously we want to keep that number as small as possible. Now, just a word on the features. These are actually the mathematical description of the features. They're actually not very unusual. This is something that has been observed in other papers on this topic. What's important, though, is that we have simply 4 features that determine the vast majority of the variability and the descriptors that are needed in this case. And one that has not been used very often is actually the streamline curvature. That in fact, in this case, is quite important. And so these are just one way to parameterize the data set, and we use the sort of a relatively large number of features, but in a reality, only few of them are quite critical. Now, just to give you a very quick view of what the results look like, as I said, these are the results I was showing you before. So these are envelopes, uncertainty envelopes computed without using any data. And if we actually use our new data-driven prediction, which is based in the same way, we run 3 additional predictions. We compute the mean and max of those predictions, and we build these envelopes. So the methodology is very much the same. It's just that now the perturbations are parameterized using the random forest. And so they are evaluated locally, and they're different locally. And as you can see now, we have envelopes that are much, much smaller, and they are reduced exactly where the original model, basically they better represent the distance between the experiments and the original baseline model. So in a sense, they are really now driven towards what is expected to be the true uncertainty of the model, rather than all the potential range of modeling that we can see in our setting. Okay, so just to give you a sense of what these perturbations look like, on top you see the picture that we had originally. So everywhere the perturbations are homogeneous. They're applied independently of the location or the features of the flow field that you have. On the bottom, you see that the perturbations are actually much larger, close to the bottom surface, and tend to be relatively small elsewhere, which is, again, an indication of the fact that most of the uncertainty comes from the specific characterization of the separated region, but also wherever the turbulent intensity, so the flow field is relatively well behaved without problems related to turbulence, there is no need to introduce perturbations. And so this is sort of the message here, that once again, we're not trying to build a better model per se, we're trying to understand how much potential uncertainty there is. And in the absence of information, the potential uncertainty is actually quite large. But if you can bring some data to the description, and in this case, the data is actually quite relevant, the uncertainty becomes very, very small. Okay, so this leads me to the last slide. What I wanted to say is that as I started from, we started to build these models by try to understand from a theoretical perspective what is that we can say on turbulence models that is ground on mathematical basis. So the concept in this case is that the Reynolds stress tensor is mathematically well understood as an object, and the type of matrix that we have, the type of tensor that we have in that case, enables us to use an eigenspace decomposition and identify bounds and limits for the eigenvalues. And that's quite important because it provides some information about the range of possible models that we can build out of the baseline model without having to introduce any additional assumption. But as I said, the challenge is really the fact that unless we bring in some information or perhaps make some additional assumption hypothesis, we cannot parameterize that space of the models in any way. So any model in that space, in that triangle, at least that I depicted earlier, is as likely as anybody else, as anyone else, unless, as I said, we introduce additional assumptions. Now, we have done both the prediction of these uncertainty envelopes without introducing assumption, what I've been calling data-free, but also through the introduction of a machine learning model that predicts that perturbation, how much perturbation is likely given a specific set of features that we encounter in the flow field. And in this case, we have seen that the expectation of reducing the uncertainty because we're introducing data is quite effective, and it's not unusual. It's not I would say it's not very different from what you typically do in an updating or in a Bayesian updating setting, for example. But it's interesting because it provides you a very nice direct way to understand also the importance of the value of the data that you're bringing in, because you start from a data-free prediction, so you get these sort of large envelopes, and if the data that you're using for the training are not very effective in characterizing the uncertainty, then the envelopes are basically remaining not really changed that much. And so this is in that indirect way a good test and a good set of a good procedure to really understand the value of information that you're bringing in. Now, we used random forests as a simple strategy. One of the things I wanted to bring up in closing is the fact that the ultimate goal is to perform online simulations. And so for that, we need to have first a model that is still computable, that doesn't really introduce too much nonlinearity or too much complexity that then affects the numerical solution procedure that we have in our standard simulation codes. And it turns out that compared to, for example, a deep neural network, random forests tend to be much more amenable to this kind of solution procedure. So the nonlinearity that is introduced is perhaps more benign, I would say, than not a full DNN. This is one side. The other piece, though, is the cost. So we are performing an evaluation of a random forest per every cell. For every computational cell, we have to compute these perturbations, and every iteration of our nonlinear procedure, the equations remain nonlinear. So we need a Newton solve to solve the equations. And so it turns out that the cost is actually quite a bit of a driver in these cases. When we started this work, just as an anecdotal evidence, it turns out we were trying to do our best in terms of the training testing of the random forest, and we were using something like 500 trees and a relatively complex or a relatively general sort of framework for the regression. And it turns out the cost was 3-4 times larger than the original baseline calculations. Now, still not very much because the original calculation was inexpensive, but quite intolerable if you think of the goal of this simulation, that was simply to replace the original simulation with uncertainty envelopes. Now, it turns out that as we went down this route and reducing the trees and simplifying the regression model, we are now able to compute the envelopes and the type of simulation with a cost that is only 15%, 20% larger than the baseline, which is, again, an important consideration thinking about the online implementation and use of these methodologies. Now, the next step, I'll finish here by saying that we are continuing to work on generalization, try to understand how to train and test the model using different data sets, and specifically how to combine different data sets. It turns out it's very typical to have a relatively different representation of turbulence based on different configurations and different settings you might have. For example, flow separation is clearly a major driver, but effect of rotation, effect of buoyancy, or perhaps other characteristics might lead to very, very different data sets, and not necessarily an easy way to combine all these data sets into one single training exercise. So we are exploring that, and we are using the idea that random forests are already ensemble learners. So in a sense, there is a way to actually build a more general ensemble learner that will be able to use data from different sources. And then the final step that we're working on right now is to actually build not only the data-driven envelope, but also a data-driven best prediction. So this is not to replace the original model, but to inform what is the closest representation of the data in terms of a model that we have. And so this will sort of complete the picture, because at this point you'll have a baseline, you'll have data-driven envelopes. Sorry, you have the baseline, you have data-free envelope, then you go to data-driven envelope, and then a best estimate as well. And so this is sort of the full picture we have in mind, and we're almost there. We're sort of concluding that as we speak. So I'll stop here. I'm happy to answer any questions. This work is actually now published in Journal of Propulsion just very recently, and I'm happy to answer any question or to have any discussion at this point. Thank you.
All right. Well, thank you very much, Gianluca, for the very nice talk. So for the audience, if you like to type in your questions, you can do so, I believe, in the chat function, which is just at the bottom, at least in my screen on the Zoom. But I can try maybe, I have a few questions actually, but just to start off the questions, I have a question about the DNS data. So basically you embed more information on your discrepancy function through a reference solution. In this case, DNS, direct numerical simulation, we can consider as the truth in some sense. But and then we learn the discrepancy function through the random forest. But does it extrapolate then to other cases, or is that that discrepancy function is only constrained in that specific DNS case? So how generalizable, if you like?
Yeah, that's a great question. And I honestly, I must say, we are at the very beginning of the generalization. I would say that certainly the overall framework is only trying to reduce the envelopes. And so when it fails, the reduction is actually not very, very extensive. And so in that sense, the issue with generalization is a little bit less severe than if you were actually trying to build a predictive model directly, because in that case, you obviously, any mistake or any lack of generalization will lead into an error. In this case, leads to an over prediction of uncertainty. So having said that, though, I must say that this is actually a pacing item. Understanding how to pick your data is a major question. As I mentioned before, we know already that we actually have been trying cases, for example, with high-speed jets. This is our second case of interest. And what we're seeing is that the training from a separated low Reynolds number flow, so the low-speed flow, compared to a jet actually leads to very different parameterization. So the most important parameters, the most important features that represent one are actually not very important for the second. And so this is a fundamental question that we're asking ourselves. And at this point, as I said, we're still exploring different way of doing it. But the interesting observation is that if we train with the wrong data set, so if we train for a separated flow, say with the jet case that has no separation, what we are seeing is that the impact on the uncertainty envelopes is basically minimal. So the data-driven envelopes are basically still equivalent to the data-free envelope. And so at least we have a way to have a sense of the generalizability from this sort of observation, right? We're not starting from scratch and just building the envelopes. We have a data-free envelope that is always there, is always available. And so the comparison with that helps us with generalization. But I would say that's a start of an answer, but it's not a full answer yet.
All right. Well, thank you, Gianluca. So there is a question from Ashley. So following on the question about generalization, the one we were discussing, since the random forest might have some uncertainty on its own predictions, do you foresee a benefit to quantifying this uncertainty and incorporating that uncertainty into the perturbation constraints and therefore final uncertainty bounds?
That's a really interesting question. So absolutely, that's something we've been looking at. Now, as you might know, the conventional view of uncertainty quantification is a probabilistic view. So it requires you to have basically a model that statistically represents a probability of say, some input parameters and how they map into the output. And so we actually have started to do that. The challenge, though, is once again the computational cost, because this means, as what we have seen right now, are basically a very, very limited number of simulations that are used to build these envelopes, right? And we're talking about 3 or 5 simulations. That's basically all you need. Now, as soon as you start adding a probabilistic component to that, now the number of simulations obviously increases enormously. You know, you might not need to go all the way to a Monte Carlo sampling, for example, but even just more parsimonious ways, like, you know, collocation or other strategies, still require quite a bit of simulations. So we are trying we're sort of bridging these two disciplines very carefully, not to blow up the amount of simulation and cost we need to carry out. But you're absolutely right. For example, for DNNs, we have been studying the effect of uncertainties exactly in this way, you know, as it's typically done with these techniques. And it's certainly possible to include it. It's just a question of the computational costs you're willing to spend to do that.
Okay. Oh, thank you. And David, they are asking, right. So they're asking about the possibility to narrow the uncertainty envelope, which resonates with what we were discussing. So they're asking about the possibility to narrow the uncertainty envelope, but David guesses that you kind of answered that with the best estimated prediction about to be finalized. I'm not entirely sure about the question, David, if you want maybe to clarify. But basically, yeah, I think the question revolves around how to minimize the uncertainty envelope, I believe.
Yeah, I think the interesting thing is that in my opinion, at least, it's all dependent on data. I think you can obviously have a better predictor. Say you can train the random forest in a better way. You can use more trees, or you can use a completely different strategy and sort of build a better predictor. But at the end of the day, the amount of reduction that you have from the data free to the data driven has to do with the relevance of the data. How much the data that you have is actually relevant for that case. And in a sense, that's obviously the challenge, because we might not have the correct data, the most appropriate data for the problem of interest. And so just to give you a sense, I think the way we are sort of envisioning this sort of moving forward is that you'll have independent sets of say, random forest trained on different data sets. And then because this is a very, very, very cheap computational effort or very limited computational effort, you can actually build envelopes based on different data sets and different corresponding trees. And then the question really becomes how you combine this envelope into one. And in many ways, that's going to be the critical element. If you're familiar with weak learners, this is kind of the idea that we have in mind, right? That each one of these is a weak learner in the sense that it's very, very specialized, but then the combination of all these weak learners might provide a good way to build a more sensible envelope that generalizes as well. But as I said, this is now, I'm really going to sort of projective work. We haven't really focused too much on that yet. We're Jan is really working on that right now.
Right. Well, thank you. So Mark is asking a question about deep neural networks,
Yes.
since you mentioned them. And do you have any sense of the level of nonlinearity that is present in the model? So he's wondering whether it could, old-fashioned kernel methods be suitable for the task?
Yeah, that's a great question. Actually, my answer is I believe so. I haven't tried them, but I believe so. I didn't mention this before, but one of the reasons why we are focusing, for example, on random forests rather than DNNs is because one of the objectives is to actually extract a model eventually. So the intention is not necessarily to continue to use machine learning as a tool in practice, but eventually sort of distill it down to perhaps some semi-analytical perhaps model that we can use. So I think that, and in that sense, I sort of, I'm hinting to the fact that perhaps kernel method might be a good choice as well. Certainly going to the complexity of trying to embed more information into a very complicated machine learning model, very extensive DNN or something like that is not really the direction we're thinking of going anyway, because that will create something that potentially is certainly more opaque and not really meaningful in terms of usage at the end. Especially, as I said, we're trying to build an understanding of what these uncertainties are. And having more transparency, more simplicity would certainly help. But at this stage, I don't have a very precise characterization of the nonlinearity. So it's still more based on our experience in using them and how sort of complicated the numerical procedure become that allows us to have a sense of how much nonlinearity we're introducing. But we haven't really focused on understanding more quantitatively what that means.
And which is very relevant to this question and answer you gave, Salvatore. They are asking whether you thought about using Gaussian processes to learn the discrepancy function. And my question would be also, why didn't you choose Gaussian processes, or why do you think the random forest is the winning tool?
Yeah, I would say these are all obviously good choices. In many ways, I think, as I said, given that we're striving for simplicity, I think it's very likely that we'll sort of all this strategy eventually will converge to something that is relatively simple. I think the dichotomy in many of machine learning approaches have to do with trying to be more and more sort of predictive and adding more information into those models. We're going in the other direction. And so I do think that eventually many of these ideas will sort of converge towards a simpler formulation. I don't know exactly, we started from random forests, just part of our experience. We sort of had some experience using them within this framework. So it was a more natural choice. But I agree with you. I think there is potential to use other strategy, Gaussian processes or other strategies that, as well. And as I said, going towards simplicity, I think will also benefit perhaps these techniques more than other more sophisticated machine learning techniques.
And Tim, they're asking about experimental data. So the question is if you have available experimental data, could you use them to develop basically the ground truth for your task?
Yeah, that's a fantastic question, and actually this is the motivation for us going towards this idea of weak learners and building ensemble of models. We certainly want to use experimental data, as you know very well, experimental data don't come with the richness of details and features and sort of amounts that we can use, for example, from numerical simulations. And so in that sense, we, rather than taking experimental data from different sources, dump it into one set and then train a model, our intention is really to use the best model for each data set and then combine the models, rather than combine the data sets. So absolutely, and we're already working on that. The jet case I was mentioning earlier, that's a NASA experimental data sets that we're using for the jets. And that's absolutely the intention. I mentioned, high fidelity simulations are very advantageous. You can obviously build your own data sets and so on, but there are limitations. There are limitations in terms of conditions that you can use, in terms of parameters. And so experimental data are really a useful support as well for this work. And we wanted to make sure we can include that as well.
Mm-hmm. Okay, well, thank you. I had actually another question. So about my understanding is that you are assuming somehow that the model itself to be quite good, and you want to reduce as much as possible the uncertainty of that specific model, right? So, and at some point you were perturbing the Reynolds stress, if I'm not mistaken, with a term like the perturbation term EIJ, I think it was. Mm-hmm. Are we making any underlying assumption on the bias of the original model? Like, are we making an assumption that the model is completely unbiased there, or are we not?
So that's a good question. So we are, in a sense, trying to really characterize all the possible biases that the model have. I mean, the idea of perturbing towards the three sort of corner state is to say that we can bias the model differently and then observe what kind of results we get from that original model. So in a sense, what we are characterizing is really the bias of the model. Now, as I said, in the absence of data, we can only bias it towards sort of the extreme states. And that's exactly what the data-free model is. Now, are there assumptions? Well, there are assumptions, yes. Although we are using this idea of eigenspace perturbations, we know something about the orientation and the shape, meaning the eigenvalues and the eigenvectors. But you might, remember from the beginning, I had also the trace of the tensor, right? The kinetic energy. It turns out we are not touching the turbulent kinetic energy. There is a mechanism that we're using to characterize the production of kinetic energy. That's a physical quantity we can bound. But there are other terms in those equations that are not really, represented. So we're still sort of assuming that the error introduced in that kinetic energy transport is small compared to all the other uncertainties. So, and that's obviously useful and important in cases like the ones that I showed you, where we know that the turbulence production mechanism is mainly through mean velocity gradients, is shear driven. And so we know that assumption is actually correct. But as you go, for example, to buoyancy driven flows, where the mechanism of production of turbulence has nothing to do with mean shear, then this approach is not going to be very convincing in that setting. And so we'll need to worry about the additional assumption in that model for kinetic energy. But it is, this is sort of, we are trying to sort of build a foundation that eventually allows you to incorporate also these additional effects. But as it is now, it's really for shear driven turbulence.
Mm-hmm. Okay, well, thanks. Did you gain any physical insight on what the discrepancy function is telling us? You showed a nice picture towards the end about the non-homogeneous spatial perturbation, and it was very high at the wall, in the separated region. And
right.
Can we also learn more about the physical?
Yeah, that's exactly what we're trying to do right now. We have a limited number of features that are important, and so in a sense, what I was describing before, the idea that we might be able to actually describe them with some sort of an analytical expression is something that we are looking at right now. So that, out of this process of learning, rather than using the machine learning per se, we can actually perhaps characterize that directly in terms of these features, sort of explicitly in terms of these features. In terms of physical understanding, that's a little more difficult because, again, we're not after a better model. We are after a sort of a reduced uncertainty. And so in that sense, I'm not too convinced that we can attach a lot of meaning to these envelopes. It might be simpler to sort of look at this best estimate eventually. That's something also we're looking at, where perhaps in that case, a physical meaning will be valuable. But for the envelopes, I doubt that we can really learn too much about the physical meaning of those.
Okay, well, thank you. So we are almost close to 5 p.m. in UK at least. Is there any other question from the audience? Please feel free to type it in the Q&A panel if you like. Right, it seems, well, I have a ton of questions, but maybe I will follow up.
Sounds good.
Actually, I will read up the paper, this paper you are showing in the slide. So that sounds quite interesting.
And we're hoping by the end of the summer, there will be a second one coming out that has more details on this best prediction model as well.
Excellent. Is there other final questions for Gianluca, for Professor Iaccarino? Okay, I think, yeah, we can also wrap up here if everybody has no questions, and very happy to close. Gianluca, thank you again for your nice talk and also the nice discussion. I hope I can again follow up later, and yeah, see you either in Italy or in Stanford someday, or in England.
Sounds good. Thank you for having me. Appreciate it.
Thank you. Bye bye.